This is SpaceTime Series 21, Episode 40. Coming up on SpaceTime. New evidence shows the first stars formed just 250 million years after the Big Bang. Dark energy's impact on life in the multiverse. And the Juno spacecraft's spectacular new view of Jupiter. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have discovered evidence that the universe's first stars formed just 250 million years after the Big Bang. The findings, reported in the journal Nature, are based on the detection of oxygen in a galaxy known as MACS 1149, JD1, located some 13.28 billion light-years away, the most distant known source of oxygen ever detected. Although the presence of galaxies at this epoch is no longer surprising, the detection of oxygen in this galaxy leads to a far more remarkable conclusion. You see, there was no oxygen when the universe was formed 13.82 billion years ago. Only hydrogen and helium, together with trace amounts of lithium and beryllium, were created in the Big Bang. Oxygen was only formed after the first stars in the universe created it through the fusion of primordial hydrogen and helium. And this first oxygen was then only released into space to form gas clouds in galaxies once those very first stars died and exploded as supernovae. So the presence of oxygen at this time in this ancient galaxy indicates that a previous generation of stars had already formed and died at an even earlier time. The research team, led by Takuya Hashimoto from the Osaka Sanyo University, detected a signal of ionized oxygen in observations by ALMA, the European Southern Observatory's Atacama Large Millimeter Submillimeter Array Radio Telescope in Chile. The infrared light initially emitted by the oxygen had been stretched to microwave lengths by the expansion of the universe before it reached Earth and was observed by ALMA. Meanwhile, neutral hydrogen emissions from the same galaxy were independently detected, confirming the distance using the European Southern Observatory's VLT, or Very Large Telescope, also in Chile. That distance of 13.28 billion light-years corresponds to looking back in time when the universe was just 500 million years old, which is just 3.5% of its current age. Meanwhile, the authors reconstructed the star's formation history in the galaxy using infrared data taken by NASA's Earth-orbiting Hubble and Spitzer space telescopes. The observed brightness of this distant ancient galaxy matches models suggesting the onset of star formation would have occurred about 250 million years earlier. Those models indicate that star formation in this galaxy became inactive after a first ignition, and then revived at the epoch of the ALMA observation some 500 million years after the Big Bang. Scientists think that the first star formation probably blew a lot of gas out of the galaxy, which would have suppressed ongoing star formation. However, over time, the gas returned to the galaxy, leading to the second burst of star formation. And the massive newborn stars in this second burst ionized the oxygen from the first burst of star formation. And so it's those emissions which have now been detected by ALMA. You're listening to SpaceTime. I'm Stuart Gary. A new study shows that dark energy probably has far less impact on the development of the universe and life within it than previously thought. The findings, reported in the monthly notices of the Royal Astronomical Society, suggest that life could potentially be more common throughout the multiverse. The multiverse is this cosmological hypothesis in which our universe is only one of many. Think of it as a single bubble in an unending ocean of foam. Questions about whether other universes exist as part of a larger multiverse, and if so, whether they could harbour life, are burning issues in modern cosmology. And the key to answering this question is dark energy, that mysterious force causing an acceleration in the universe's rate of expansion out from the Big Bang 13.82 billion years ago. Scientists say that current theories on the origins of the universe are predicting far more dark energy across the cosmos than what's actually observed. The problem is, adding larger amounts would cause such a rapid expansion of the universe that it would dilute matter before any stars, planets, or even life could form. And that's where the multiverse theory comes in. Introduced in the 1980s, it can explain the luckily small amount of dark energy in our universe that enabled it to host life among many other universes that could not. Using huge computer simulations of the cosmos, the authors found that adding dark energy up to a few hundred times the amount currently calculated to be present in the universe would actually have only a very modest impact on star and planetary formation. And this opens up the prospect that life could be possible throughout a wider range of other universes, that is, if they exist. The simulations were produced under EAGLE, the Evolution and Assembly of Galaxies and Their Environments project, one of the most realistic simulations of the observed universe ever developed. The authors wanted to know just how much dark energy there could be before life becomes impossible. Their simulation showed that the accelerated expansion driven by dark energy has hardly any impact on the birth of stars, and hence places for life to arise. It seems even increasing dark energy many hundreds of times might still not be enough to make a dead universe. However, the results were unexpected and could be problematic as they cast doubt on the ability of the theory of a multiverse to explain the observed value of dark energy. According to the research, if our universe is just one of many in the multiverse, then we'd expect to observe much more dark energy than what we do, perhaps 50 times more than what we actually see in the universe. Although the results don't rule out this hypothetical multiverse, it seems that the tiny amounts of dark energy in today's universe would be better explained by an as yet undiscovered additional law of nature. Professor Grant Lewis from the University of Sydney says mystery still surrounds what dark energy is. Scientists know that about 68% of the total mass energy budget of the universe today is made up of dark energy. That leaves around 27% to be made up of that equally mysterious substance called dark matter, and just 5% to be made up of baryonic or ordinary matter, the things we know about, such as stars, planets, asteroids, people, and cars. But think about that. The fact that 95% of the cosmos consists of mysterious unknown particles and forces raises serious questions about science's understanding of the universe. In fact, the use of the term dark in describing dark matter and dark energy signifies science's total lack of enlightenment about what these things are.
We don't know what dark energy is. It's required to understand how we observe the universe and we see the universe, the expansion accelerate, and we need something in there, but we don't know what that stuff is. And there are some ideas that it's related to the quantum mechanical nature of empty space. So there's this idea that you get, in quantum mechanics, particles popping in and out of existence, and that popping in and out of existence basically puts a base level of energy into even empty space, and maybe that is responsible for the dark energy that we see in our universe.
This is what we see in the Casimir effect, things like that.
Yes. So it's not just crazy quantum dreaming. This is actually something that's observable in physics. We know that the vacuum has to have this kind of property because if we don't include it in quantum calculations for things even as simple as the hydrogen atom, we get the wrong answer with regards to our experiment. So there is this base level of energy there. We just don't understand if it's the stuff that's responsible for accelerating the expansion of the universe.
Is it fair to think of it sort of simply as the opposite of gravity, which occurs in mass?
Look, I'll say yes in a very hand-wavy way. If I had some physicists looking at me now, they'd be giving me some strange looks. We try to be careful with terminology. This is the source of something to do with gravity, and it produces accelerating space-time. So it a little bit like anti-gravity, but it's said in a very hand-wavy way.
The other issue there is, could it be simply our position in the universe from what we're seeing when we look at cosmic scales? That would depend on where we are. If we're actually in the middle of a void, which we're not, but if we think there's now a possibility we could be at the edge of a void.
Yeah, so of course, when we have our observations, which the famous observations that were at the end of the 1990s, which resulted in the discovery of the accelerated expansion, the simplest explanation was that we needed to add this other substance to the universe that gives this accelerated expansion that we see. Now, other theorists have sat down and said, well, maybe that our view of the universe, as you mentioned, is not the same as everybody else's. If we're in the region of the universe which is emptier than the general universe, then we'd expect to see that expansion as well, a similar kind of accelerated expansion away from us because we're sitting in the middle of a void. The problem is at the moment is that we don't have a very good description of gravity acting on large scales whereby we can calculate accurately what we'd expect to see in a void. So we use some very simple models, but so we don't know. We don't know. There's definitely some people that think that maybe it's the structure of the universe that's given us this signal. Other people think it's something to do with the substance of the universe itself.
Okay, and using all this as a foundation, we now move on to the research that you guys have been involved in.
With a good colleague of mine, Luke Barnes, we've been studying this question of fine-tuning in the universe. Why do the laws of physics allow for the existence of atoms and molecules, eventually planets, etc.? And what you find is that if you mess around with the basic laws of physics, it's very easy to basically kill a universe. You can get universes where you don't get atoms forming, where stars don't burn, etc. One of the questions we asked ourselves is, what about the amount of dark energy that we see in our universe? Because if we do our theoretical calculations, we do our quantum calculations of empty space, the prediction for the amount of dark energy that we should have in the universe is huge. There's this ridiculous number, 10 to the 120, which is 1 followed by 120 zeros. The theoretical prediction for dark energy is that much larger than what we actually see in the universe.
Yeah, the universe should be a lot hotter than what it is because of this.
Well, essentially, if the universe had been born with its natural amount of dark energy, the expansion would have been instantaneously super fast, and matter would have thinned out, and there'd be, one hydrogen atom per observable universe, or even less than that. So, if we were at the natural amount, then the universe would be sterile. So the question we had is, why do we have this little sliver of dark energy, which is only now really becoming apparent in our universe? Because if we had more of that, it would have wiped out the possibility of there being life in the universe. And so this then relates to this concept of the multiverse, that our universe is essentially one of many different universes which are out there in the multiverse. And even though we don't understand the process by which universes come into being, that when a universe is created, that there's some sort of cosmic roll of the dice, and the laws of physics are written into the universe at the moment the universe is created. So in the multiverse, the idea is that you'd create many, many individual universes. Each one would have its own particular set of laws of physics. And in most of those universes, they would be sterile because you wouldn't be able to form atoms, etc. And in many of those universes, the amount of dark energy that you would have would be far too much to create planets and stars. So maybe that's the natural explanation. Maybe we with a cosmic roll of the dice, we got the very small amount of dark energy, which allowed planets and stars and eventually life to form. But the question that we have is, just how big is the range of acceptable amounts of dark energy that you could have in a universe and allow it to form beings that could observe the universe? So that's essentially what we wanted to focus on. And this has been a question that people have looked at for several decades now. So there was a famous paper by Nobel Prize winner Steven Weinberg back in the 1980s where he did some back-of-the-envelope calculations and just showed that, too much dark energy is a bad thing. But we've gotten to the state now where we can actually build synthetic universes on a computer. So we can actually go back, revisit the calculations as done by Weinberg, but this time put in a lot of the messy laws of physics that are needed to form stars. And so for stars, you need to have gas clouds, they need to collapse, they create stars, and then material gets recycled. So in our synthetic universes, we can actually put all of that stuff in. And so what we thought we would do is, why don't we just build a suite of synthetic universes with different amounts of the cosmological constant in there, the dark energy, and see what the effect is on the growth of galaxies, which is something you need to form to have stars and eventually planets. So essentially that's what we did. We built a series of synthetic universes, and you need supercomputers to do these calculations because, you're following huge quantities of mass over a large amount of time. And we looked where the material ended up and whether or not you could form objects like galaxies in which you could have stars. And essentially what we saw was that the range over which you can have hospitable universes when just messing around with the amount of dark energy was actually quite broad. We found that we could put about 100 times more dark energy into the universe than we see, which is small compared to the natural value, but much bigger compared to the amount that we see. And you would still form galaxies that have gas, that can form stars, and could potentially host life. So we're sort of seeing is that the multiverse must have universes not too dissimilar to our own, which are relatively hospitable. So it's not that having too much dark energy automatically shuts down the possibilities of life, that there's actually a slightly broader range than what we'd expected.
As the universe evolves, the amount of dark energy or the strength of dark energy, that seems to be changing as well, and it has been for at least the last 6 billion years.
Yes. So this is one of the curious things about dark energy. Firstly, let's think about what happens to matter in the universe. So matter is composed of atoms, etc., and you have your dark matter. As the universe expands, the density of material must drop because the material is thinning out. So over the history of the universe, what you have is that the amount of matter is continuously decreasing in terms of its density. Now, one of the weird things about dark energy is that it has a constant energy density. It's just related to empty space. So if you make more space, you make more energy, so the energy density stays the same. What we see in our universe is that at the start, matter was the dominant component, but over time, roughly over the first half of the age of the universe, matter dominated, but its density decreased and decreased and decreased until we got to a point where the densities of matter and dark energy were roughly the same. And now we've reached a point today where only 30% of the universe's energy density is in matter and 70% is in dark energy. And so as we go into the future, the impact of dark energy is going to continue to increase as matter continually thins out. That happens essentially in all of our model universes, is that at the start matter dominates, but if you put more dark energy into the universe, it comes to dominate earlier and earlier. And what we found is that there's still enough time at the start of the universe to get all the bits and pieces in place in galaxies to form stars, even with 100 times as much dark energy in there. But eventually dark energy comes to dominate and then separates the galaxies apart.
And eventually, I guess, from that, we get the big rip.
Yeah, well, see, that's another interesting question, because I said we don't really know the detailed properties of dark energy, and if it has a particular kind of relationship for its fundamental properties, it could be something called phantom energy. And look, astronomers love to give these things scary names, I know, but phantom energy is this thing which drives the expansion even faster and faster and faster until, as you said, you get the big rip, which is when essentially the cosmic expansion will start pulling individual objects apart. So first galaxies, and then individual stars, and then planets, etc., etc. At the moment, we don't know. All our measurements seem to put us on the knife edge between dark energy being friendly to the universe and just continue to drive expansion, and or to be phantom energy, which would lead to a big rip. So at the moment, I said we don't know which side of the knife edge we're on.
Either way, it's still disconcerting whether it's a big freeze or a big rip. I guess we'll have to wait and see.
Yes. There's very few happy stories in the long lifetime of the universe, I'm afraid, but that's what our laws of science are currently telling us. The entire question of the multiverse is an interesting one in scientific fields, because it makes some people very uncomfortable, because we are now essentially thinking about universes that we would never have contact with.
Yeah, how do you prove it?
Yeah, how do you prove it? And so, this has led to some people suggesting that what we might need to do is redefine science at some level to consider the impact of things that you can't directly test on our universe. And that's what we're trying to do, is trying to work out where our universe would sit in the multiverse. If somebody has an idea of how the multiverse operates, where does our universe sit? Is it a rare thing? Is it something that would be easily made? And trying to bridge this more philosophical discussion into a scientific discussion. Can we make predictions about our universe if it does sit in a multiverse? But yeah, it's a very messy area at the moment. So as I said, some people get very upset when the multiverse is mentioned. Other people feel very comfortable with the concept.
I guess one of the things that always bothered me when I hear any scientist say, well, how come the universe we live in is so finely tuned for life to have formed? To me, that always comes across as someone saying, isn't it amazing? That hole in the ground was just the right shape for a puddle to form in it.
Yes, yeah. So look, we call that puddle thinking,
yes.
Right? So this is related to the anthropic principle, man's place in the universe. And, here we are on Earth. I'm a creature. I have bones which are strong enough to support me against the pull of gravity. Isn't that amazing? What kind of creature would I be if that didn't happen? But of course, I have to have bones this strong because I evolved on this planet, and that's where my bones came from. This is the environment that I sort of live in. But the fine-tuning argument is slightly different, right? So the fine-tuning argument, if you want to consider the puddle example, it's not how amazing is it that there's a hole that the puddle fits into. It's how amazing is it that there's a hole and that there's a puddle to go into the hole. Because in a universe in which I mess around with the fundamental forces, I could stop the nucleosynthesis of the elements, and so I could make sure that there are no stars. No stars mean no oxygen. No oxygen means no water, so there goes your puddle. And no heavy elements means you don't get any soil or ground or rock, so you don't get a hole to put the puddle in. So I can even shut down puddle making in the universe by messing around with the fundamental forces. And they said that's very, very easy to do. You can end up with a universe which you cannot have any complexity. And what I mean by that is that you have no chemistry, right? We are chemical beings, and we are formed out of a set of 92 building blocks that stick together in certain ways. And those building blocks are a signature of the fundamental parts of the universe, the fundamental forces, the fundamental masses, and you mess around with them and you no longer have them. So you don't get a universe with puddles and holes in it if you mess around with the fundamental forces. So it's a deeper problem than just worrying about puddles fitting into holes.
Of course, the thing with fundamental forces is we don't really, and dark energy is the best example of that, we don't really know how many fundamental forces there are likely to be.
Well, that's true. And of course, this is actually one of the great things of science, right? We take our laws of science as we have them, and we push them, and we try to understand the universe around us. But every scientist knows that tomorrow something may happen, which means, we go, I need to take all those calculations and check them out because there is this extra force, or there is this extra interaction, or there is this, or there is that. And scientists are prepared for that, but we can work with what we've got to make predictions. That's one of the strong points of science. Scientists are very good at changing their minds as new bits of evidence come along.
That's Professor Grant Lewis from the University of Sydney. And this is Space Time. I'm Stuart Gary. The latest data from NASA's Juno spacecraft has revealed more stunning images of Jupiter, the solar system's largest planet. The new data is based on observations undertaken by Juno during its close flyby of the Jovian South Pole back on April 1st. It includes an animation showing the evolution of swirling features in the gas giant's atmosphere and a composite mosaic image of Jupiter's cloud tops. Scientists also produced a 3D infrared movie flying around the planet's northern polar regions, depicting densely packed cyclones and anticyclones. Juno's principal investigator, Scott Bolton from the Southwest Research Institute in San Antonio, Texas, says he's stunned by how amazing the Jovian cloud tops are. Jupiter's polar storms comprise multiple cyclones at each pole, rather than having just a single polar vortex like on Earth. The observations found as many as 8 giant cyclones moving simultaneously around the Jovian North Pole and at least 5 around its South Pole. Juno's also provided scientists with their first detailed view of the dynamo powering Jupiter's magnetic field. Scientists were able to produce new magnetic field models from measurements made during 8 of the probe's orbits around Jupiter. From these models, they derived maps of the magnetic field both at the surface and in the regions below the surface where the dynamos thought to originate. Because Jupiter's a gas giant, the, in brackets, surface is defined as 1 Jovian radius, about 71,450 kilometres. At this point, hydrogen becomes conductive enough to be dragged into near uniform rotation by the planet's powerful magnetic field. You see, deep inside Jupiter, the high temperatures and crushing pressures transform Jupiter's gaseous molecular hydrogen into an exotic form of matter known as liquid metallic hydrogen. The new data shows that Jupiter's magnetic field is totally unlike anything previously imagined. The field, which is about 10,000 times stronger than anything on Earth, contains unexpected irregularities. It looks lumpy, stronger in some places and weaker in others. The map of the dynamo source region reveals areas of surprising magnetic field intensity, and that Jupiter's magnetic field is more complex in the northern hemisphere than what it is in the southern hemisphere. In fact, about halfway between the equator and the North Pole lies an area where the magnetic field is incredibly intense and also has positive polarity. But this is flanked by areas with less intensity and with negative polarity. And that's where it's different to the south. You see, in the Jovian southern hemisphere, the magnetic field is constantly negative, becoming more and more intense from the equator to the poles. Scientists are still trying to figure out exactly why they'd see these differences in what, after all, is a rotating planet that's generally thought of as being more or less fluid. The uneven distribution suggested the magnetic field may be generated fairly close to the surface, possibly just above the metallic hydrogen layer. Of course, Jupiter's magnetic field generates the biggest and most powerful aurora in the solar system. While Earth's aurora are triggered in response to solar activity, Jupiter makes its own aurorae through the energy generated by its magnetic field, which uses induced electric fields to accelerate particles to the poles where the auroral lights get displayed. Meanwhile, another instrument, Juno's microwave radiometer, which measures thermal microwaves radiating out from deep inside the planet, are hinting at structure hundreds of kilometres beneath Jupiter's thick swirling cloud tops. Juno's gravity experiments already shown that Jupiter's iconic belts and zones rotate as a series of cylinders down to depths as much as 3,000 to 5,000 kilometres, below which Jupiter may be rotating as a rigid body. Juno mission scientists have also taken data collected from the spacecraft's Jovian infrared auroral mapper GIRAM to generate a three-dimensional fly-around of the Jovian North Pole. Imaging in the infrared part of the spectrum, GIRAM captures light emerging from deep inside Jupiter, equally well night or day. The instrument probes the weather layer down to 50 to 70 kilometres below Jupiter's cloud tops. GIRAM also senses the temperature of Jupiter's atmosphere, with temperatures ranging from -13 to -83 degrees Celsius, providing an insight into how the powerful cyclones at Jupiter's poles work. GIRAM also senses the temperature of Jupiter's atmosphere, with temperatures ranging from -13 to -83 degrees Celsius, in the process providing an insight into how the powerful cyclones at Jupiter's poles work. The imagery will help scientists better understand the forces at work in the animation, a North Pole dominated by a central cyclone, surrounded by 8 circumpolar cyclones with diameters ranging from 4,000 to 4,600 kilometres. Got to remember, before Juno, scientists could only guess what Jupiter's poles look like. But thanks to Juno's close polar flybys, scientists now have these detailed infrared images of Jupiter's polar weather patterns, showing these massive cyclones in unprecedented spatial resolution. Scientists have also developed a new understanding of the planet's interior composition and how deep the interior rotates. The data shows that the zones and belts which we see in the atmosphere rotating at different speeds extend down about 3,000 kilometres from below the visible cloud tops. The hydrogen becomes conductive enough to be dragged to near the uniform rotation of the planet's powerful magnetic field. Juno is studying Jupiter's weather, atmosphere, internal composition, cloud structure, gravity, magnetic and auroral fields. The findings will allow scientists to better understand how Jupiter formed. And as the gas giant contains more mass than the combined mass of everything else in the solar system, other than the Sun, by studying Jupiter, scientists will learn more about the evolution of the whole solar system. Juno's on a highly elongated 53 Earth-day orbit designed to avoid as much of Jupiter's intense radiation belts as possible. Juno has now logged well over 200 million kilometres, completing some 11 science passes since entering Jovian orbit back on July the 4th, 2016. Juno's next science pass will take place later this month, on May the 24th. I'm Stuart Gary. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. And in case you haven't heard, the interwebs have been running at absolute fever pitch about a new audio version of that famous "What colour is this dress?" debate that went viral a couple of years ago. So, what are you hearing? Laurel or Yanny?
Laurel. Laurel.
Your answer could depend either on the quality of the sound system or speakers you're using, or on your level of hearing loss. You see, it's all got to do with frequency. The audio clip sounds like Yanny if the soundbite's being played at higher frequencies, and Laurel if it's being played at lower frequencies. And that could be caused by the settings on your earbuds, speakers or headphones. Or on the other hand, you could just be getting old and it could be due to hearing loss. You see, as people get older, they start to lose their ability to hear high frequency ranges. That's why kids love using those high-pitched mosquito ringtones that can usually only be heard by people under 25, making them inaudible to parents and most teachers. For the record, 56% of people thought they heard a man saying the name Laurel, while 44% thought it was a woman saying the name Yanny. As for me, well, at first it always sounded like Laurel, but after a couple of times, I thought I was distinctly hearing the name Yanny. And for the record, the correct answer is Laurel. Now, if all this sounds incredibly familiar, I'm sure you all remember the infamous dress, that photograph that went viral in early 2015, when people engaged in wild debates over the colour of a single dress. People looking at exactly the same image would see either a black and blue dress or one that appeared white and gold. The phenomenon revealed differences in human colour perception and sparked numerous scientific peer-reviewed studies. The photo originated from a washed-out colour image of a dress posted on Tumblr, which quickly triggered over 10 million tweets and countless comments on other social media platforms. The dress itself was eventually confirmed as being a royal blue lace bodycon dress from the retailer Roman Originals, and yes, it was blue and black in colour. The differences seem to stem from the way different human brains perceive colour and chromatic adaptation. That is the way brains adjust to changes in illumination in order to perceive the appearance of an object's colour in daylight. As for me, well, I was a bit of an outlier. To me, it usually looked sort of sky blue and chocolate gold in colour. But it also seemed to occasionally switch to blue-black as well, all of which probably says an awful lot more about the way my brain works than what I should be admitting on air. New research suggests that long exposure to traffic-related pollution significantly increases the risk of asthma, especially in early childhood. The findings, reported in the Journal of Allergy and Clinical Immunology, are based on studies involving 1,522 Boston area children between 1999 and 2002. Scientists looked at how behavioural and environmental factors, such as sleeping and eating habits or exposure to pollution, impacted children's health. They found that children living less than 100 metres from a major road were nearly 3 times as likely to have asthma and needing daily medications by the ages 7 to 10 compared to kids living more than 400 metres away from a major road. While physicians have long known that smog and pollution can bring on an asthma attack, researchers remained uncertain about what role long-term exposure to certain pollutants might play in the development of the disease in children. In America alone, some 25 million people suffer from asthma. It's a chronic lung disease which has been on the rise, especially in Western civilization, since the 1980s. A new study says limiting global warming to 1.5 degrees Celsius would save the vast majority of the world's plant and animal species from climate change. The findings, reported in the journal Science, reveals that limiting warming to the ultimate goal of the Paris Agreement would avoid half the risks associated with global warming of 2 degrees for plants and most animals, and 2/3 of the risks for insects. Species across the globe would benefit, but especially those in southern Africa, the Amazon, Europe and Australia. Reducing the risks to insects is especially important because they're so vital for ecosystem services such as pollinating crops and flowers and being part of the food chain for other animals. This is the first study to explore how limiting climate change to 1.5 degrees Celsius would benefit species globally. The researchers, which included scientists from James Cook University, studied some 115,000 species, including 31,000 insects, 8,000 birds, 1,700 mammals, 1,800 reptiles, 1,000 amphibians, and some 71,000 plant species in what was the largest scale study of its kind ever undertaken. Archaeologists on the Palestinian West Bank have unearthed a rare ancient coin dating back more than 2,000 years. It was discovered by a joint archaeological team in a cave some 30 kilometres northwest of Ramallah. The coin was minted either in the 3rd or 4th year in what's known as the Bar Kokhba revolt by Jews against the Roman Empire, which lasted from the years 136 to 134 BCE. One side of the coin shows a palm tree with 7 fronds and 2 clusters of fruit, as well as the inscription Shimon. The other side portrays vine leaves with 3 lobes and the inscription to the freedom of Jerusalem. Alongside the coin, archaeologists also discovered pottery fragments and glass vessels which can be dated to the same period. The coin was discovered during a multi-university archaeological survey of various historical digs in the West Bank. Archaeologists believe the items would have been brought into the cave by Jewish refugees who were forced to leave their homes and hide there at the height of the revolt. The Bar Kokhba revolt was a rebellion by Jews in the land of Judea led by Simon Bar Kokhba against the Roman Empire. It took elements of 6 Roman legions to finally crush the rebellion. In an attempt to erase any memory of Judea, the ancient land of Israel, the Emperor Hadrian wiped the name Judea, the land of the Jews, off the map, moving its inhabitants into slavery and dispersing them to the far reaches of the Roman Empire. The entire region was then renamed Syria Palestina by the Romans, of which the ancient land of the Jews became modern-day Palestine. It's now been revealed that at least 147 million people had their personal details compromised during last year's massive Equifax credit reporting agency data breach. Equifax has been forced to disclose the total number of people affected, as well as exactly what data was hacked in its report to the US regulator, the Securities and Exchange Commission. The information Equifax lost to hackers included social security numbers, names, dates of birth, mailing addresses, driver's license details, phone numbers, email addresses, credit card numbers, and credit card expiration dates, as well as other personal details. Closer to home now, and the personal information of thousands of Australians, including women seeking abortions and contraception advice, have been compromised by hackers targeting Family Planning New South Wales. The Reproductive and Sexual Health Organisation has been forced to email 8,000 clients, warning them about the ransom cyber attack targeting its online databases. With the details, that's of the attack, not what's on the databases, we're joined by Alex Zaharov-Reutt from IT Wire.
Yeah, now this is an Australian government organisation called Family Planning New South Wales, probably something similar to Planned Parenthood in the States. And they use a Drupal-based content management system from a company called Acquia, which is Boston-based. And there were a couple of breaches or vulnerabilities that were discovered in the past month or so. And the family planning website didn't have these patches applied in time. And the cyber hackers came along and tried to put ransomware on the site, tried to ask for $15,000 in local currency, or sort of the equivalent of one Bitcoin, and said that if you don't pay us, we'll wipe your site. Well, the government had backups of the site, thankfully, and wiped it themselves, and the hackers didn't come back. But the government department says that the information of 8,000 people had been stolen. It was just contact information, they say. They say it wasn't actual medical records, which were stored on a different system. I guess the scary part is that, even if you're on the ball and people are able to close down vulnerabilities as quickly as possible, the bad guys these days are working fast. And who knows what they've done with this data. This then leads to the question, if you can't necessarily trust the organizations to have applied all the patches or to have adequately encrypted all of the data, even if it's just basic contact information, let alone private records, what can you do as an individual to try and protect yourself from the inefficiencies of others?
Indeed.
So what I would suggest here is that you can use a VoIP service, which gives you a landline number but delivered over the internet. So it's not the same as the number that you have had at your home through your copper wires for years and years, but an internet phone number that you can buy a local number. You can buy a local number anywhere in the world. I have one through my Skype service that anywhere I'm in the world, if someone dials that number and I have an internet connection, then my mobile phone will ring, but they're ringing me through a landline. So you can use those. I have heard of disposable mobile numbers in some countries. You can even get yourself a prepaid, and you can get one of those prepaids that you can pay a certain amount, less than $50 or even less, and it can last for an entire year because you're using that for incoming calls, not for outgoing calls, because you probably have a different number, your normal number for that. And then you can use a mailing service. I use a service called MBE, Mailboxes Everything. It's a US company that expanded to Australia some couple of decades ago, and it gives me a physical street address that couriers cannot refuse to deliver to, which can be the case with PO boxes.
Yeah, that's a big problem with post office boxes, isn't it?
Part of the reason is because they want a signature, or they want to be able to say that they delivered it to your house, and a post office box obviously doesn't do that. But with this MBE service that I use, and there are others, USPS or FedEx, other companies offer these sorts of mailing services where you can have an address. Well, you can use that address for some of these other things that you do online that you don't necessarily want people to know your main address. I mean, you can have your main address for your bank account and your phone bill and, your license, for example, but you can even have your mail redirected at a relatively low rate per month through your local post office, that they will then send this mail either to a PO box or to one of these other mail services. And so, you sort of have to think about, well, if I can't trust others to protect myself, how can I protect myself? And yes, sadly, these services do cost extra money above and beyond what it costs to have your normal phone and your normal house address. People probably need to start considering, so that if there is a data breach, at least they're not getting the keys to the kingdom, as it were. I mean, we even have a situation in Australia, and this is probably happening elsewhere around the world, where people are trying to port your mobile number out from underneath you. In Australia and in the States, if you want to take your mobile number from one carrier to another, whoever's giving them a better deal. And in Australia, there's been this phenomenon of late where bad people are targeting your number and they're porting it across to a different service. So they're taking
port means import, okay.
Yeah, import. They're taking it from one provider to another, and they've somehow been able to glean your date of birth from social media. They've stolen your address from somewhere, and they have your name. and they probably found out your mother's maiden name from social media. And so that's all the information you need to be able to port a number from one service to another. And then once they have that, they can then activate the two-factor authentication. I forgot my password, or they send.
Who was your first teacher, and what was your first car, and what was your dog's name?
A lot of banks will say, look, we'll send you an SMS, right, with the code that you need to log in. So they've been tracking you and stealing your username and password for your bank, and then they now have your number where they can get that second factor. I mean, personally, I use Google Authenticator. I don't have anything, if I can, SMSing me a password anymore, or some sort of digits, because you can have your number stolen from you, and then people use this to drain your accounts. So you've got to sort of be one step ahead of the bad guys as much as you possibly can.
Alex Sahara-Roy from IT Wire reporting. You're listening to Space Time. I'm Stuart Gary, and that's the show for now. You can subscribe and download Space Time as a free twice-weekly podcast through Apple Podcast iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from spacetimewithstuartgary.com, or from your favourite podcast download provider. Spacetime's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., and available around the world on TuneIn Radio. If you want more Spacetime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary, at Spacetime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. This has been another quality podcast production from Bytes.com.